Question 11. In an experiment to demonstrate the photoelectric effect, light of different wavelengths was shown onto the metal surface of a photoelectric cell. The maximum kinetic energy of the emitted electrons was determined for the various wavelengths and recorded in the table below. So we are given the inverse of the wavelength versus the maximum kinetic energy. 11.1. What is meant by the term photoelectric effect? So this is the process in which electrons are ejected from a metal surface when light of suitable frequency is shown on the surface. Draw a graph of EK max on the y-axis versus the inverse of the wavelength on the x-axis on the attached answer sheet. So I've already drawn that. If you draw your graph correctly, it should be like this. So I've simply just plotted the graph using the maximum kinetic energy on the y-axis and the inverse of the wavelength on the x-axis. Use the graph to determine the threshold frequency of the metal in the photoelectric cell, and then 11.3.2 Planck's constant. So we need to understand what's really happening here so that we can be able to apply that onto the graph. So our graph looks like that, where on the y-axis we have EK max, and then on the x-axis we have the inverse of the wavelength. This is given by 10 negative 19 joules, and that is given by 10 to the exponent of 6. We have a graph that looks like that. So our graph looks like that. Okay, so what we have there, since this is the inverse of the wavelength, it means that we have the threshold wavelength at this point right here. And the reason why I'm saying that at this point here, this is the threshold, it's because all the points to the right of this point right here, we are experiencing kinetic energy, meaning that we have overcome the minimum energy that is required in order to move an electron. From here all the way to the left, the kinetic energy was 0. So we hadn't overcome the minimum energy that was required in order to move electrons. Okay, we have this equation right here. So I want us to modify this equation so that it becomes a representation of the graph. The graph is on the y-axis. No, the maximum kinetic energy is on the y-axis. So this is going to be EK max, which is going to be E minus the threshold frequency. So this becomes y is equals to mx plus c. So we can see that y is a representation of the kinetic energy. The gradient, we must find the gradient, and then c is the y-intercept. E is given by hc all over lambda minus wo by 1 over the wavelength minus the threshold, the work function. This is what we have on our x-axis. So the whole of that becomes x. Our gradient, which means our gradient is equals to hc. And then our y-intercept is the work function. Okay, so if we were to extend that line right there, somewhere wherever it cuts on the y-axis, that is where we would have our work function. It's very important for us to understand this. 11.3.1. They say that we should use the graph to determine the threshold frequency of the metal in the photoelectric cell. So there's a couple of ways that we can do this. You can manually extend that line right there on the graph that we currently have. You can extend there and see where it cuts. But I prefer to use the calculator because it is more accurate. So I'm just going to use the stats function. So I'm going to say mode setup 2 for stats, and then I'm going to choose option 2, which is going to be given by a plus bx. So I'm going to input my data. My x is the inverse of the wavelength, so that's the 5, 3.3, 2.5, and the 2. My y's are the maximum kinetic energy, 6.60, 3.30, 1.70, 0.7. And then when I'm done, I'm going to press AC, Shift 1, and I'm going to choose option 5, which is regression. So A should be equals to negative 3.21, and B should be equals to 1.965. This right here is the same as the equation of a straight line. So this is y is equals to b x plus a, which is exactly like that. So b represents my gradient, and then a represents my work function. So we know that the work function should be equals to HFO. 3.21 times 10 to the exponent of negative 19. It is times 10 to the exponent of negative 19 because we know that in the y-axis, the unit should be times 10 to the exponent of negative 19, which is equals to Planck's constant FO. Therefore, the threshold frequency should be 3.21 times 10 to negative 19 over 6.63 times 10 negative 34. So I'm getting 4.84 times 10 exponent of 14 hertz. This is option 1. Option 2, we can use this equation. E should be equals to the work function plus EK max. We know that E is equals to HC all over lambda, and then we know that's HFO plus EK max. I'm not changing this because we are given EK max there. So H is 6.63 times 10 to the negative 34. C is just the speed of light. Now, if you look at this very carefully, H over lambda, this is the same as saying C multiplied by 1 over lambda. So the value that we have there, we're going to substitute it exactly as it is, because that's 1 over lambda. So we're going to substitute. You can pick any 2 points. It means that if you choose the inverse of the wavelength, which is 2.5, you're going to choose the kinetic energy of 1.7. If you choose 5, you're going to choose 6.60, and so forth. So I'm going to choose the first one. So it's 500 times 10 to the exponent of 6, because the units are times 10 to the exponent of 6. So this is 6.63 times 10 negative 34. Okay, let's just use WO here, the work function, so that we make our work easy. And the EK, that's 6.60 times 10 to the negative 19. 6.63 times 10 to negative 34, 3 times 10 to the exponent of 8, and then 5 times 10 to the exponent of 6. So all of this should be minus 6.60 times 10 to the exponent of negative 19. So I'm getting 3.345 times 10 to the exponent of negative 19 joules. But we know that WO should be equals to HFO. So this is 3.345 times 10 negative 19, 6.63 times 10 negative 34 H, which is FO. FO should be equals to 3.345 times 10 negative 19 34. So I'm getting 5.04 times 10 to the exponent of 14 hertz. These are the two methods that you can use. So 11.3.2. Use the graph to determine Planck's constant. Okay. We know that gradient should be equals to change in y over change in x. And the reason why I'm doing this is because we've already established that, you see, Planck's constant is part of the gradient. So I know that the gradient must be hc. And then this is going to be change in EK max over change in the inverse. So H should be 3 times 10 to the exponent of 8. And then we're just going to choose any 2 points there. So I'm going to choose 6.60 minus 3.30. So I'm just choosing these 2 points. Multiplied by 10 to the exponent of negative 19, because those are the units. And then for the bottom one, I need to make sure that I'm choosing what matches what I've already chosen on the right hand side. So this is 5.00 minus 3.30 times 10 to the exponent of 6. (6.60) minus 3.30 times 10 to the exponent of negative 19. 5.00 minus 3.30 times 10 to the exponent of 6. So I'm getting 1.94 times 10 negative 25. H should be equals to 1.94 times 10 negative 25 all over 3 times 10 to the exponent of 8. So I'm getting 6.47 times 10 negative 34. The units for Planck's constant, I believe it's joules second.